How can the application of attractor networks serve as a foundational framework for comprehending the functional connectivity of the brain, unraveling its implications for cognitive processes and disorders? Furthermore, how can these attractor networks be employed to delve into the intricate causal mechanisms and dynamic interactions underpinning the brain's functional connectivity, drawing parallels with the quantum microprocessor architecture, thereby addressing the fundamental principles governing brain function and potential quantum information processing analogies? Additionally, what role do predictive capabilities of attractor networks play in anticipating the outcomes and consequences arising from the manipulation or alteration of the brain's functional connectivity? And how does this relate to the analogous quantum microprocessor architecture, emphasizing the need for predictive models in the development of interventions or treatments? Moreover, how can the application of attractor networks contribute to the identification and diagnosis of abnormalities or dysfunctions in the brain's functional connectivity, particularly in comparison to its analogy with quantum microprocessor architecture, signifying potential implications for healthcare and neuroscience? In evaluating the suitability of attractor networks as a framework for studying the brain's functional connectivity and its relation to behavior and cognition, what are the discernible advantages and disadvantages that need to be considered? Considering the translational impact, how can attractor networks be instrumental in designing or developing interventions? Considering the translational impact, how can attractor networks be instrumental in designing or developing interventions and treatments for disorders or impairments of the brain's functional connectivity, especially in comparison to their analogies with quantum microprocessor architecture? Addressing the diversity and variability in the brain's functional connectivity across individuals, groups, and species. How can attractor networks be modified or extended to enhance their applicability and generalizability in different contexts, taking into account their analogy to quantum microprocessor architecture? Moreover, how can the empirical validation of attractor network models be conducted experimentally to establish their reliability and accuracy in explaining the brain's functional connectivity, aligning with their analogy to quantum microprocessor architecture? Furthermore, in the realm of artificial systems or devices, how can attractor networks be leveraged to simulate or emulate the intricate features and functions of the brain's functional connectivity and its analogy to quantum microprocessor architecture, potentially revolutionizing the development of more efficient and intelligent computing architectures? Delving into the realm of generating novel insights and hypotheses, how can attractor networks contribute to advancing our understanding of the brain's functional connectivity and its analogy to quantum microprocessor architecture? Comparatively, what are the notable similarities and differences between the attractor network model and the quantum microprocessor architecture concerning information processing, storage, and retrieval? Elucidating the potential connections between classical and quantum information processing in the brain. In exploring the robustness, flexibility, and efficiency, how does the microprocessor architecture of conventional computers differ from the brain's functional connectivity? Shedding light on the distinctions between biological and artificial systems, thereby contributing to advancements in computing and neuroscience. Moreover, how can attractor networks be employed to compare or contrast the brain's functional connectivity and its analogy to quantum microprocessor architecture with other biological or physical systems or processes, offering broader insights into the uniqueness of the brain's functional connectivity? In the pursuit of comprehensive evaluation, how can attractor networks be utilized to develop metrics for evaluating the quality and quantity of information processed, stored, or retrieved by the brain's functional connectivity and its analogy to quantum microprocessor architecture, essential for validating attractor network models? Finally, considering the evolutionary aspects, how can attractor networks contribute to explaining or understanding the evolution or development of the brain's functional connectivity and its analogy to quantum microprocessor architecture, providing insights into the emergence and development of complex cognitive functions? While being mindful of the challenges and limitations inherent in using attractor networks to model the brain's functional connectivity and its analogy to quantum microprocessor architecture,